Section 2, Video 2. So let's take a look at an example. In this particular case, we're looking at a square root. Now in the past, we would find the prime factors of 27. But what we're going to do now is we're going to change our methodology of simplifying these. Again, for the hopes that we can handle much larger numbers in the roots. Now, what we're going to use is a very important rule that says that if I have the square root of two things being multiplied inside it, I can separate them and put them in their own roots. Now this is very important. Now we know that when we have two roots being multiplied, we can go this way. But we also need to understand that we can go the other way. So if we have two things being multiplied in a root, we can separate them and put them in their own little roots. I like to say in their own houses. And that's important because when we do our work here, we're going to use that. So when we see 27, we're going to change our goal. Instead of being the prime factors of 27, we are going to ask ourselves, what's the largest square perfect square that goes into 27? The first square is 4. That's 2 squared. That does not go into 27. The next one would be 9. 9 does, but again, we want the largest one. So the next one would be 16. That's 4 squared. That doesn't go into it. 5 squared is 25. That doesn't go into it. So the best number is 9. So we're going to write this as 9 times, in this case, 3 then. And we are going to rewrite x cubed as x squared, because we want it's square root, so we want to group them in 2's. And we have x. Now, I'm going to rewrite this as the square root of 9, the square root of 3, the square root of x squared, and the square root of x. Now, we know the square root of 9. It's 3. We know the square root of x squared, it's x. And these two we cannot root. So they are left inside the root. And this is your simplified answer. Again, you can get this the same way by doing your prime factorization, but this method is a process we want to get comfortable with so we can handle very large numbers, even though I know we could do it without it here. Next one, we have a number out front. Now that's going to wait, so keep that in mind. This is going to sit and be waiting at the end. So we look at 448 and r to the 4th. Now what is the largest number, the largest perfect square that can go into 448? So what I would do is I would look at my list of perfect squares that's on the top of this page, and I see that the largest one I have written down, and there's many more, is 256. Well, 256 can't go into 448. And I go down that list and I divide 448 by each one, and nothing works until I get to 64. Now notice I started with the biggest one working to the smallest because I want the largest square that goes into it to be the most efficient. So if I work my way down, I find out that 64 goes into it. Seven times. And I'm going to rewrite r to the 4th as r squared and r squared. Now I'm going to write them as square root 64, square root 7, square root r squared, and square root r squared, which gives us 8. It gives us an r and an r, and root 7 stays there. So our final answer would be 8r squared root 7. Now one key piece we have to remember, there was a negative 5 sitting there. So that negative 5 is on the outside waiting to be multiplied. So in other words, I should have had that right here waiting. So what is 8 times negative 5? Negative 40. And then we have the r squared root 7. So that is our final answer. So again, when it's a big number, a lot quicker to do it that way than doing the prime factors. And this ends Section 2, Video 2.